A2 further maths, simple harmonic motion. Okay, so what I'd like to do is just consider this situation. The weight is attached to the spring. Now the spring is at rest, it's not moving at all. So because it's not moving, then we can say it's what's called its equilibrium position. So that spring sits without moving at its equilibrium position. Now what I'd like you to do is consider this. I put some force on the bottom of that weight. I lift it up in the air. Okay, so I start to squash in that spring. Then what I'm going to do is I'm going to just make a couple of assumptions. I'm going to assume there's no frictional forces acting at all. Okay, so there's no air resistance, there's no loss of energy either, so no loss of energy through heat or sound or anything like that. So therefore, what would happen? What would happen when I let go of that weight? Now, what you probably consider is if you let go of the weight, it would end up moving down. Okay, it would end up moving down, wouldn't it? But then at some point, the weight or the tension in the spring would overcome the weight and therefore pull it back up again. And then what you end up with is this situation. So the tension in the string manages to pull the weight back up, but then it's squashed, there's a thrust force, and so on. Now, if we actually had that situation without any loss at all, then what you would say is that it would oscillate indefinitely about that equilibrium position. It would just keep oscillating above it, getting squashed, and therefore it pushes it down, therefore it stretches it, so it pulls it back again, and it oscillates continuously. Now that example there that you can see is an example of what we call simple harmonic motion. All right, something that's oscillating continuously like that is an example of simple harmonic motion. Right, so the next thing I'd like to do is just consider this. If you plotted a graph, so the position of that weight over time, okay? So if we imagine we start a clock just there, what would you see if you plotted that weight's position over time? Okay, that's what I'd like you to consider. Okay, so what would the graph actually look like? Well, hopefully you sort of thought about it like this, right? It goes up to its top position, it slows down, but then it comes back down, noticing that its actual velocity at the top goes to zero. Then it comes back down to the bottom, velocity is zero, where the force is overcome, and so on. And so it produces that lovely wave function just there. And if I said to you now, what type of wave is that? Hopefully you could tell me it's a cos function or a sine function. It's a cos or a sine function. Most likely a cos, because we started at the top just there. Now, so a cos function would fit neater in that one. If it started from the equilibrium position, it's more likely to be, it fits nicer with the sine function, although either would work. Okay, so I've got this function just here. I've got my graph just plotted there. And from time equals naught, that's what the simple harmonic motion would look like. All right, so let's just put a couple of bits of notation in here. The time it takes to start at the top, go all the way to the bottom, and then back up. Okay, so from there to there is called what? So if I'd ask you just what it would be called if it was a sine or a cos graph, all right, from the maximum point to the next maximum point, hopefully you'll tell me that is to do with its period. And that's why when we talk about this simple harmonic, this motion here, it's called its periodic time. All right, because it's to do with time. The ones you did in your normal maths aren't necessarily to do with time. It's maybe to do with angles. So therefore it's just called its period. In this case, because it's to do with time, we call it its periodic time. The time it takes to return to whatever position it was before. It doesn't have to just be the maximum point, of course. It could be this point just here. It goes past that point just there, but then goes back to it there. That is its periodic time. Now, the periodic time can be calculated by using that formula just there. And don't worry, you'll get time to put all these formulas down in a little while. It's better just to try taking them in at the moment. So if we consider what that's talking about, well, 2 pi is one full rotation. So that's when it's gone from the start position to back to its start position. That would normally be the period of the sine or cos graph. Okay, but we're dividing it by this function here, what we call omega. All right, we divide it by omega, and therefore we get the periodic time. Now the omega value basically represents how many cycles, how many complete cycles you could fit within 2 pi seconds of time. That's what it means. All right, but you need to just learn that formula just there. All right, so we'll come back to that. I'll get a chance to write down your notes in a minute. So what else can we tell? We can also work out things like the maximum distance. Now the maximum distance is from the equilibrium point is either there, just at the bottom, or when it just reaches its equilibrium point there, just there where the velocity equals 0 again, and that would be its maximum height. Now both of those distances are the same. The distance from the equilibrium point to the minimum point, or the distance from the equilibrium point to the maximum point, are the same distance. Different displacement, but same distance. And we call that the letter A. Now that means that we've got an amplitude now, which we call A. We've got a periodic time, which was 2 pi over omega. So what that means is I can now work out the equation of this curve in terms of A and omega. Okay, the displacement would be what? How would you write that down? Okay, so think back, pause there, try to do this bit yourself. How would you write the equation of that curve just there, which has a period of 2 pi over omega? Okay, so hopefully you managed to get something similar to this. Its position at any given time equals the amplitude times by cos omega t. And of course, at the maximum point, that cos omega t is going to equal to 1, because that's its maximum point for a cos function, which is why its maximum is a. It can't ever be greater than 1, so x can't ever be greater than a. The omega part just there, as you know, if I'm trying to work out its period at any given time, then you can do it 1 over, which is where the omega cancels out with the 2 pi's cancel out. So you end up with omega t. Right, so well done if you managed to get that displacement equation. Okay, just one thing that's worth noting is it does depend on where you start position, which one fits better. I said earlier on, you could write this as a sine wave, you can, all right, you'd end up with that minus 90 degrees. But you can also, but it's neater in cos. But if you started at the equilibrium point, and let's say pushed it up, gave it an initial force to push it up, it would bounce up, and then bounce back down, and oscillate like that. In which case, it is better to think of it as a sine omega t. You're only going to be given one of those two. All right, it will only start at the equilibrium point or at the maximum or minimum point. It will not start anywhere else. Okay, so we're going to give them one of those, although the equations work for any starting point position. So when I mentioned this a few times, but it's just worth just mentioning it again. Then we do know that the velocity equals 0 when it reaches its maximum point. So it's to do with its velocity. So when it reaches its maximum point just here, a bit like when we talk about throwing a ball in the air, velocity equals 0, and then it starts to accelerate and starts to gain its velocity again as it goes up, slows down, reaches 0 again. So just be aware that the velocity equals 0 at the maximum minimum point, because you may need it. Okay, so the velocity of a particle that moves under simple harmonic motion, this is where you need to just grab your notebook. Let's put down some of these key facts that we just noticed then. Okay, so I took you through and showed you where they came from. You guys just need to learn them off by heart. So the displacement from the equilibrium point is x equals a sine omega t. Okay, so we just saw where that equation came from. I did it with cos. I said to you, you can do it with sine. We're dealing with it with sine now. So you've seen both. So if I'm starting from the equilibrium point, then that would be the equation for the displacement. Notice it's starting from the equilibrium point. If it's starting from the maximum point, change sine to cos. What I'd like you to do is try this yourself and get it down your notebook first, but try it yourself just on a rough piece of paper. Could you work out dx over dt? I expect you all to be able to do that. Okay, so hopefully you just differentiate this. Do not forget that you differentiate in terms of t, and omega can be thought of as a constant. Once that's found, that's set for that spring. So therefore we could write it as a omega cos omega t. We can work out the velocity like that. Now what I'm going to do is I'm just going to play with this a little bit. So I know that the cos function, okay, or the cos function can be squared and then square rooted. Now the reason why I do that is because I want a cos squared. I'm also just dragging in the a value. If you're thinking why is he dragged in the a value but not the omega, it's because I'm going to be using this function in a minute. And this function has got the a on the front. I could have had omega squared under there. That would have been fine. Right? I just don't need it. Right, you'll see in a second. Just don't need it under there. So this a squared cos squared omega t. So all I've done is squared it and then square rooted it. I've made it quite complicated. Why have I done that? Now, hopefully you notice that you could do it because cos squared is 1 minus sine squared. So I could rewrite this as a squared times by 1 minus sine squared. So that's where the a squared times 1, minus a squared times sine squared omega t. So I've got that equation just there. Now, why would I do that? Oh, because a squared sine squared omega t is exactly the same as x squared. So really, I could rewrite the velocity as that. And don't forget that omega and the a squared would be given to you in the question or figured out in the question. That is just the constant for that spring, and that, or the constant for that harmonic motion, and that is your maximum point. So that's a link between the velocity and the displacement, as opposed here where it's a link between the velocity and the time. You need to be able to show and use that equation just there. Okay, pause if you needed more time to get it on your notes. Right, so we're going to look at the acceleration as well. We'll do both. All right, so same situation, but this time instead of velocity, I want to look at the acceleration. All right, so get it down, pause it, have a go yourself. Okay, so differentiating it once was easy enough. Differentiating it twice is not more difficult. So hopefully we're going to get down to being able to differentiate twice. But the problem is normally we'd use A, wouldn't we? We'd use A for acceleration, but we have an A in the question. So if you wrote it down, you differentiate and change it to V, and then wrote A equals A something, okay? We'll see what it is in a second. Then you've got A equaling A, which doesn't really make any sense. So what we want to do is we want to change to a different type of notation. Now the different type of notation that we're going to use is this sort of notation. X with 2 dots above it. Now what that means is that you've differentiated the x value twice. And this x double dash function is used a lot in simple harmonic motion. All right, a single dot could also be used. Okay, so a double dot is for a second derivative, whereas a single dot is for the first derivative. And there's absolutely nothing wrong with using that notation for velocity. You could have it as x, x dot, x double dot, instead of x, v, and a. Okay, there's absolutely nothing wrong with using these. And of course, we've also used dashes to represent it. There's lots of different notation to show the differentiation. It depends on which mathematician was using it at the time. But you can use, or you should use for simple harmonic motion, this idea of x double dot dash. X double dot. Okay, so we'll use that now. So if I differentiate it twice, yes, I've got the velocity. So I've differentiated once, that would be my x dot. And that's what I just saw. But then when I differentiate a second time, I'm going to get this. So that's my x double dot, my acceleration. So I can write that as x double dot equals this. Now notice that I have omega squared sine omega t. Now that, forget the omega squared, is a sine omega t. Now the a sine omega t is exactly the same as the starting position. X equals a sine omega t. So therefore, I end up with that equation just there. And it's probably worth noting that it didn't matter if I'd started with cos. Okay, and in fact, in the previous one as well, when I was doing velocity, didn't matter that it was cos. So previously I used 1 minus cos squared equals sine squared. Well, you'd use the same idea in the previous one, and you'd get exactly the same answer. And it's exactly the same with acceleration. If I started with a cos omega t, I would still end up with exactly the same equation down here to either I started with sine. Okay, so it's just worth noting. Now that equation at the bottom is an important simple harmonic equation. That's the key one that you need to notice. That if I differentiated the displacement vector twice, it's always equal to minus omega squared x. That shows simple harmonic motion just there. Okay, so a particle that moves under simple harmonic motion has that equation. Right, so if you can show that the equation, the motion can be written in that form, Therefore, you can state that it has simple harmonic motion. But you also need to be able to recall and use these results as well. Okay, either of those two as a start position. It might be worth in your notes just highlighting that starts at the equilibrium, that starts at the maximum point. Okay, so it's just worth noting both of those. But just in your notes, that's the starting equilibrium, that starts at the maximum point. You may also, if you've got a bit of a mean examiner out there, you may have questions which involve you starting at the minimum point, which of course is just going to be minus that one. Okay, so once you've got the displacement, you also have to get velocity. And velocity is that equation just there. Yes, it's that one and that one differentiated, but it can be written in this form. And this is the one I said, it doesn't matter which one of these you start with, you always get that same equation there. Okay, so that same equation is regardless of time and it's regardless of your starting position. That is always going to be your velocity. Okay, and then the final one is just making sure you know what the periodic time is. Alright, so time is 2 pi over omega. So that talks about what omega is. So you may have a situation where you've got periodic time, and because you know what periodic time is, you could do 2p over 2 pi, over periodic time equals your omega value. So therefore you could write your simple harmonic motion in that form. Okay, so there is a link between those two. So you might be given periodic time and therefore work out this one. Just making a note of the two important bits. So the A is the maximum distance, T is the periodic time. Right? Omega is just this constant that we use throughout. Okay, so pause there if you just need more time to get it down. And I'm just going to cover another key fact that's important. Notice this equation just here is important. And the reason why this equation just here is important is because it doesn't have anything to do with time. It's a link between velocity and displacement. Okay, and same with this equation just here is a link between acceleration and displacement. It's got nothing to do with time. Right, so we're just going to look at another situation down here. So I know that's a key fact. Okay, that x double dash is exactly the same. X double dot, sorry, is exactly the same as the second derivative. That's what that means. Okay, so highlight it if you haven't got that written down yet. That the double dot means a second derivative. But this second derivative here is in terms of time, right? Which is a bit messy because I don't want anything in terms of time. My equations aren't in terms of time, so I don't really want this in terms of time. Okay, that's what that one's in terms of. So once I've got that, what I can say is, well, if that's in terms of time, I can actually change it to change in velocity over time. Okay, that's what that is, isn't it? Change in position over time, differentiate twice. But the first time you differentiate gets you dv over dt. All right, so sorry, the first time you differentiate gets you v, and then I differentiate velocity to get acceleration. So really that is the same as that. Now if that's true, which it is, then what I can do is I can change this by using chain rule. Because really, I could write that as it's the change in position over the change in time times by the change in velocity over the change in its position. Notice the dx cancels out, leaving you dv over dt. Now why would I do that? Well, this bit just here, change in x over the change in time, is just velocity. So you could write the second derivative here, the x double dot, as v dv over dx. It's worth just noting that down, that fact, because you may need to use it. Okay, you may need to use it if you've got something like a velocity in terms of x. Right. Okay, pause if you need more time to get anything down. Right, so let's have a look through a simple harmonic question together then. And what we're going to do is I'm just going to break it down to the individual questions that you've probably got as an A, B and C parts in the actual question itself. Okay, so this question says this. A particle is moving in a straight line with simple harmonic motion. So we've got a situation potentially like we saw before. A weight on a spring is bouncing either side of the equilibrium point. Its displacement at time t seconds relative to a fixed origin on the line x meters. So it's talking about the line changing or the displacement changing over a given time. So everything's pretty much the same as what we saw earlier on with our spring. What we have noticed is they actually give us an equation just here. So they're giving us a second order differential equation. Now the first question could have been given to you earlier on when we were just looking at second order differential equations. They're just saying to you, look, this is a solution just here. I want you to check it for me. Can you verify that that equation there works in this second order derivative? Okay, so that's what I'd like you to do first of all. All right, so pause there and just check it works. Okay, so whether you're writing this question down or you're just taking your time and going through it, it's up to you. But hopefully you've have a go at some of the parts yourself. So hopefully you've noticed that you can differentiate x twice. So there we go, differentiate it once, differentiate it twice. And then if you substitute that part into there and that part into there, what we notice is actually it is correct, isn't it? This is a correct equation because I can substitute it in and therefore end up with 0 as the solution. Now what the problem is, of course, is that that equation just there has both the cos and the sine in it. Now the ones we looked at was either that part or that part. But that's okay, because what we'll find is that A or B in a minute is probably going to equal to 0. All right, and that tells me whether it starts at the top or whether I start in the middle. Okay, so there's my final statement. Yes, it is definitely a solution. It works. Okay, it's a possible solution. So let me write down x equals a cos 3t plus b sine 3. Right, give us another bit of information. So again, I'd like you to have a go yourselves to see if you can work out or show that b value equals 0. Let's do that yourselves. Okay, so hopefully you did exactly what it said. You took the t value, you substituted it in. All right, we know that the particle is at rest. Be careful. Did you substitute it straight into this one and were you wondering why the b value didn't cancel out? It's because the particle was momently at rest. In other words, its velocity equaled 0, not its displacement. So therefore, we need its velocity. What's its velocity? It's differentiating it once, so it's changing its position over time. So therefore, we got that. Then we can substitute in our t equals 0. Now the cos 3 lots of 0, well, cos is going to equal 1. So therefore, I should be able to work out what the b value is. And this part here, because the sine part equals 0, the whole of this cancelled out, leaving me 3b equaled the velocity. But velocity was 0 at that point. So I've got 3b equals 0, therefore b must equal 0. Okay, so 3b equals 0, therefore b must equal 0. So very well done if you managed to show that, and if you spotted that they had momentary at rest. That was the key thing that we talked about earlier on, setting the velocity equal to 0. Okay, so I've got my equation changed now. Because I know that b equals 0, then I've got my x value as a cos 3t. And again, for the wise people amongst you, you've noticed that this equation just here is the same as the displacement equation we were talking about earlier on. X equals a cos omega t. That's what we figured out before. This part, with a bit of rearranging, is definitely the same as a simple harmonic equation. Second derivative, x double dot equals minus 9x. That's the same as that. Okay, so what's the question I want you to have a go at? Given that x equals h, when time equals pi over 9, could you find a in terms of h? All right, so pause there, have a go at that yourselves. Okay, so let's see what you did then. Did you just substitute the parts in, same as before, but this time it's talking about substituting into the displacement equation. So this one is straight into there. So you could substitute the pi equals pi over 9, okay, and you could substitute in h for x, and what we find is that h equals a over 2, so therefore a equals 2h. The maximum value it's going to be is 2h. Right? Be careful. A lot of people seem to think that it's always going to be the same as that for that front bit. It's not. So not in this case. So let's substitute that in. Right? And now we've got our equation pretty much set up in terms of h and time. Okay, so let's look at another question then. Find the maximum speed of the particle in terms of h. So it's maximum speed. So pause there, have a think how you might do that. Go back to those previous equations, have a think if any of those help you. Okay, so it's maximum speed. Let's think about what's going to happen at its maximum speed. So it reaches its maximum speed. If you think about simple harmonic motion, you think about that particle moving all the way to the top, velocity equals naught, then it comes all the way back down. It reaches the equilibrium point and then it starts to slow down again to get to zero. Then it goes to accelerate and it reaches its maximum point again at the equilibrium point and then it goes up to zero. So its maximum speed is always at the equilibrium point. Okay, regardless of where your starting position is, always, if you let go of that spring, its fastest position is at the equilibrium. Right, so we know that it reaches maximum speed when x equals naught. Okay, so that's going to help me because I can work out maybe a time or something like that. So when x equals naught, 2h cos 3t is going to equal 0. That means we know that h can't equal 0 because h is the maximum height. If h equals 0, the thing's not moving at all. So h can't equal 0. So therefore I can cancel out the 2h. I can divide both sides by 2h. That leaves me the cos 3t must equal to 0. Now if cos 3t equals to 0, that's telling me that time must be pi over 6. So when t equals pi over 6, that's when this particle is getting its maximum speed before it starts to slow down again. Then it reaches it again, then it starts to slow down. So pi over 6 is the time you're looking for. Okay. Once you've got that, of course, then you can work out its maximum speed. You can work out its velocity. All right, first of all, and then just make sure you change it to a speed if it's negative. So the velocity is minus 6h sine 3t, because that's me differentiating that equation just there. So I've differentiated that equation, I've got my velocity. Once I've got my velocity, I can substitute my t in, and what I end up with is substitute that in, velocity equals minus 6h. But of course, that's a velocity. I want a speed. So its speed is going to be, ignore the minus, square it all, and square root gets me a speed of 6h meters per second. That's the fastest speed, depending on, as we said before, depending on the height, whatever the maximum height is. Okay, so again, pause before we look for the next question. Okay, so let's make it a little bit more interesting. The mass of the particle, so the particle itself is m kilograms. So now we're bringing in this extra bit of information, mass. And then they're talking about a force. Now hopefully, and it's no different to what we talk about in normal maths, if you see the words mass and force, then you should be thinking of only one equation, and that's, of course, F equals ma. So we are going to be using F equals ma at some point in this equation. Given the answer in terms of h and m, so we're looking for, find the magnitude of the maximum force acting on the particle during the motion. Okay, and of course the force is all to do with its tension. So we've got its velocity just there. Now that's no good. We don't need that in the equation. We do need its acceleration. So its acceleration at any point in its motion is calculated using that. Okay, so at different times the acceleration is at different values. But we also know that if we use F equals ma, where m is just the mass, so we can pull that m, and the acceleration we just calculated. So therefore we got that. So therefore I could write my equation as F equals minus 18 mh cos 3t. But I'm looking for when is it at maximum. Now the greatest value that this could be is when the cos 3t is itself at its maximum. Now the cos 3t's maximum, of course, is 1. So therefore the maximum force is just going to be minus 18 mh. So I could put that in, the maximum force is 18 mh or hm newtons. And the maximum force is going to be when it's at its maximum or when it's at its minimum point. Okay, so we're going to have a look at another question then. What I'd like you to do, please, is just grab your notebooks, get this one down written in your notebooks. I know it's quite long, but it's important to make sure that you've got one of these questions fully done. And then we'll have a look through it together. Now, you might want to have a go yourself, which is fine, or you might want to just work through it with me. Okay, so hopefully you've got that down in your notebook. Let's have a quick look through it. So a particle is on a straight line, A and B, so that's like maximum point and minimum point. It's travelling with just a generic simple harmonic motion. Notice that equation there is just a rearrangement of the simple harmonic equation. So it's nothing special there. They're not giving us any values. O is the midpoint. Now what's important about the midpoint, of course, is that it's its equilibrium point. Time t, so it's very algebraic, this one. Particle x meters from O. So I know that x is like the maximum point. And it's moving with a speed of v meters per second. Okay, so what I want to do then is I want to have a look through this first question. Given that A and B are the distance 3.2 meters apart, show that V equals omega lots of the square root 2.56 minus x squared. Now be very wary of just saying, because it's simple harmonic motion, V equals omega a squared minus x squared. So therefore I'm going to just substitute in my a value, and therefore that's where the answer comes from. Okay, so be very wary about just diving straight into that equation, especially if this is worth quite a few marks. Because what the examiner were expecting you to do, they probably would have hinted at earlier on, is not to use just the equation for V, but to make sure you're using this equation just here. Because I know that x double dot or acceleration there is equal to d squared x over dt squared, it's the second derivative, I could write it as v dv over dx. That I did see earlier on. Alright, I showed you where that came from. So go back over your notes, have a look. Why is that going to help in this case? Well, it's going to help because I can now substitute that back into my equation. Alright, and that's a common use of this. I could substitute it back in there. Why is it important when it's substituting there? Well, have a look at this equation just here. Okay, in this equation, that is dx squared, d squared x over dt squared. It's a change in its position over time, and then changing over position over time again. All right, so you're differentiating it a second time. So just be wary that this is to do with time, whereas this is to do with the variable x. Now what I'm doing here is I've changed it and got rid of the extra variable time in there, which has changed it from a second order derivative to a first order derivative. Right, let's just see how that's going to help me then. Because now I've got dv's, dx's, and just x's and v's in there, I can think about solving this by separating the variable. And if I separate my variables out and get that, I can bring my dx over this side. So I get v dv minus omega squared x dx. So I've got both of those. And then what I could do is I can integrate both of those. Don't forget that minus omega squared is just a number, so I could take that out if I want to. And so if I'm integrating v in terms of v, it's going to be v squared over 2 minus x squared over 2 times by minus omega squared. Okay, equals x squared over 2 times by minus omega squared, plus some constants of integration. Right, what can I do now? I can neaten it up slightly, can't I? I can times through by 2. And I could square root. So there we go. I've got a velocity equation just there. Different to that velocity equation, but at least it's getting there. There's some things that are similar. Okay, right. What do I know then? Well, I also know that the equilibrium point, right, is at O, and O to A is going to be 1.6. Okay, because O is the midpoint of AB, and AB are 3.2 meters apart. So therefore I know that O to A is 1.6. I also know that the velocity equals 0 at that point just there. Alright, so we use that in the previous question, we're using it again. That's very, very common. The velocity equals 0, right, at the maximum point. Okay, so if I've got that, what I can do is I can substitute those values in. So I've got naught equals. So hopefully I can figure out what the two c's equal to. Well, I could square both sides, couldn't I? I could rearrange and I could get that 2c equals 2.56 omega squared. Why does that help me? because now I can substitute that back in and get that. And then, just to get the exact same as this, I could take out my omega. I could square both of them, square root them, sorry, and then take them out, which gets it at the front. So therefore I get omega root 2.56 minus x squared, exactly like I required. And I've done it without just writing down the equation omega lots of a squared minus x squared square rooted. Okay, right. Let's have a look at part B then. So for part B, find an expression of x in terms of omega and t. So now that I've got my previous answer, my v value, I could then use that to work out what my x value is. Okay, so my change in x over change in time is going to be equal to this equation just here. Right, so even if you couldn't do the first bit, it doesn't stop you answering this bit. That's why they gave you this equation in the first place. They give it to you to stop you losing any more marks than just the first question. So now I've got that equals to that, I can do a bit of rearranging. I can put all the x's on one side, all the t's on the other. Now there isn't any t's, so I'm just left with this equation like this. Okay, I can separate the variables and end up with this equation. Now you might look and think, well, that's not a very easy thing to work with, but of course you should have seen this before. You've seen it recently, in that it is using a standard integral. So the standard integral I could use would be the substitution of sine. Okay, I could use that. Right, why does that help me? Well, I can see that my x value is just x, that's fine. My a value is going to be the square root of 2.56, and I've got it over 1. So therefore x equals, so that integral equals sine to the minus 1 of x over 1.6, because my a value squared is 2.56. On this side, don't forget you're integrating just a number in terms of t, so it's just going to be omega t plus, again, some constant of integration. Okay, so the particle starts at the equilibrium point O. So because it starts at the equilibrium point, I know that means that when t equals 0, okay, so when t equals 0, it says it there, by the way, if anybody's spotted, particle starts at the origin. So once you've got t equals 0, then x equals 0. Substitute both of those in, gets me c equaling 0 as well. Okay, because I know that sine to the minus 1 of 0 is 0, so therefore that's equals 0, so therefore c must equal to 0. What does that mean then? It means that I get that equation, which can be rearranged to that equation, x equals sine omega t. Therefore, that is the expression for x in terms of omega and t. That is what was required just there. Okay, notice that the a value equals to 1 in that case. Okay, so let's have a look at part C then. So for part C, given the position of the particle is x equals sine omega t, that's what I just figured out. So now I've got that. The particle completes one full oscillation. So we're looking for when it completes one full oscillation. Now I know it completes one full oscillation at its periodic time. In this case, t equals 2 pi over omega. Or the other way of looking at it is, when does this equal 2 pi? It starts at 0, finishes at 2 pi. So that's what the question is asking. When does that equal 2 pi? Well, it equals 2 pi when I substitute in my t value. So particle has a time of 8.5. Then the omega is going to be equal 4 pi over 17, or 2 pi over 8.5. But 4 pi over 17 is a lot neater. Therefore, I've got my omega value. Okay, so well done if you followed all that through. What I want you to do now is have a go at some work yourself. So pause there if you need more time. Okay, so have a go at exercise 12b. Only questions 1 to 10 for the moment, not the other questions. We'll come to those in a minute. Okay, imagine I take a spring, attach it to the ceiling, and just leave it hanging there, not moving, not oscillating, not changing. It just sits there. Okay, if I measured that spring would have what we call its natural length. Its length without any other force acting on it. Now what I'm going to do is I'm going to add an extra force. I'll add a weight to it, and the weight is the force that's pulling it down. Now, as you know, what's going to happen is it's going to stretch down. Now, I don't want it to oscillate, so what I want to do is I want to just make sure I hold it in equilibrium position and I let go, and it stays without moving. So it's in its equilibrium position. So what's important is, as soon as I added this extra force, which in this case is its mass times its gravity, it stretches by this extra x. It wants to go back up, of course. The tension in the spring is pulling it back up, but these two are equilibrium, so the weight is equal to the tension. Okay. The more force you add, the more it stretches. That seems really logical, but what's important about it is they are in proportion with each other. So whatever the force is proportional to the extension in the spring. The more force you add, the more extension you get. Okay, it seems to fit. So that's an important fact. Now the force, of course, the only force acting on it is the weight pulling down and the tension trying to pull it back towards its equilibrium position, pulling it back towards its natural length. So those two are equal to each other, the weight and the tension, because it's in equilibrium. Okay, now that T value we call a reactive force. You can be tension, but if it's pushed up, then it's also like a thrust pushing it back down. So depending on where that is, sometimes it's T for tension and sometimes it's T for thrust pushing it back down. But we can think of T as a reactive force. It's reacting to the weight that's pulling it down. Now because the forces and the extension are proportional to each other, as we said just here, I could write that as an equation, that the force pulling down equals the force pulling up, and because they're proportional to each other, the force must equal some amount of x. Force is proportional to the extension x. And that leads to this result just here. T equals kx, where T is either tension or thrust, depends on whereabouts the weight is. But that bit is always true. Okay, so the equation we just figured out, the equation we just looked at, is what's called Hooke's law. So Hooke's law is the equation that states that the extension of the spring is always directly proportional to the force within the spring, the tension, whether that's pulling it back towards the equilibrium point or thrusting it back towards the equilibrium point. It's just called the tension. So we can write the equation as T equals Kx, where the T value is that force within the spring, and the K value is a positive constant, often called the spring constant. So the spring constant, and that depends on how stiff your spring is. If it's quite a solid spring and it hardly moves, it might have a different K value, a different spring constant, to one that is quite loose and oscillates quite freely. The X is the extension in the spring. All right, so the extension beyond its natural length is what the X value is. Now, always the tension is directed towards the equilibrium point. So what that means is that when the weight is below the equilibrium point, tension is trying to pull it back up towards the equilibrium point. But if the weight was above and you've got the spring squashed, then T you could be thinking of as a thrust pushing it back down towards the equilibrium point. So the tension is always directed towards that equilibrium point. Sometimes it's helping you, sometimes it's working against you. Okay, so let's have a look at this then. A weight is added to the spring and it hangs in equilibrium at extension S. So I've set it up and I've held it, it's stopped moving, and I know that for that weight just there, that mg, then it has an x value, an extension of S. And I can call that T, and I know that T must equal some amount of S. But I also know that T must equal mg because it's an equilibrium. Okay, so I know two facts there. I know that T equals mg, but I also know that T equals some amount of S, where K is a spring constant, so it's to do with this spring. So what I can do is I can say that because it's an equilibrium, F equals ma. It's going to pretty much say what I just said, that T minus mg equals naught. So therefore, T equals Ks, but T also equals mg. So that leads to that fact that the spring constant times by the extension also equals the mass pulling it down. Right? So exactly the same, because mg is the same as tension. Okay, if the weight remains the same, but the string is stretched further, okay, beyond the natural length, beyond its extension, it goes to x. So if I let go now, as you know, what's going to happen, because it's the same weight as that, it's going to oscillate. It's going to oscillate, trying to get back to this position. So it's going to go above it, it's going to go below it, and so on. Okay, so that's what I've got a situation with. I've held it in equilibrium. That's what happened naturally. Then I pulled it further. I'm going to let go, and it's going to oscillate above there. Okay. What's important though at this stage is that force equals mass times acceleration. So that's pulling down. I've got a new tension because what's happened is there's more force. If you imagine you're pulling that spring, it's getting harder to pull because the tension inside the spring is working harder, trying to pull you back towards that equilibrium point just there. Okay, so it's different tension, but it's the same weight. Okay, it's the same weight because I've just let go of it. It's just let go. So this force pulling down is mg. The force pulling it back up is some new tension inside the spring. So I can put both of those in. Now clearly, as we know, it's not going to just sit in equilibrium because it's the same mass. It's going to be accelerating back upwards towards this equilibrium position just here. Not its natural length, its equilibrium position. Right, but what I can do is I've got a couple of facts. I know that mg is the same as ks, so I could put that in. I also know, using Hooke's law, that the tension force is proportional to these two extensions here beyond the natural length. So the s plus the x. So I know what the tension force actually is as well. Okay, I can use Hooke's law there, and I could use this bit because of Hooke's law earlier on. So I end up with that equation. What does that tell me then? Well, that tells me, after that and that cancel out, that I end up with minus kx equals mass times acceleration. All right, that leads to this result just here. That m times by the second derivative equals minus kx. Now, why that's important is that is a direct link to the simple harmonic motion that we were looking at before. It shows that Hooke's law and simple harmonic motion are closely linked. So just give you an opportunity just to get down what you need. Okay, we've put that down formally on notebooks though. So Hooke's law produced differential equations of this form. We just saw that. We saw that if we had a situation where we put a weight on, but then we added this extra stretch to it and allowed it to enter simple harmonic motion, they are linked. Now, x is the extension in the spring from the equilibrium point. Now that's important because in the previous one, when we talked about Hooke's law up here, the x was the stretch beyond the natural length. It's not that now. This x is beyond the equilibrium point. Exactly the same as when we started looking at simple harmonic motion, that x is the stretch beyond the equilibrium point. Okay, so just note that. This is different to Hooke's law. What else is different then? M is the mass. That's okay. We've got M in there, so we've got mass put in. And K is a positive constant. And as you can tell, if you just do a simple bit of rearranging and divide by mass, you can see that you've got your simple harmonic motion equation. X double dot equals minus K over M X, where minus K over M is the same as your omega squared. Okay, and that's what we're going to mention now. It can be shown that this is just our simple harmonic motion. With that simple bit of rearranging, putting the M over, then we have omega squared is exactly the same as this positive constant, right, which is the spring constant, divided by the mass. Okay, so just make sure you got down all that bits in your notebook. Okay, so let's have a look at this exam question. I wouldn't say it's straightforward, but I would like you to make sure that you've got it down fully in your notebook. And what you might want to do is have a look at when we work for the answer. We put most of this into our diagram, so you might want to miss the diagram up for a minute. Just get down some of the key facts. A, B, C, D, and E. And again, if you want to just put those down as we go through them, you can do. All right, we're going to look through each of these parts. But it's not straightforward, so I'll give you plenty of opportunity to either print that out and stick it in your notebook, or write it down in your notebook, or just reference it for your notebook. Okay, I'll pause there, give you a chance to get down what you need. Okay, so before I attempt in the questions, what I'm going to do is I'm just going to put all the information on my diagram. Okay, so I'm going to take my 2 bits of information and then I'm going to put it on my diagram, and then I can sack off all those words and just work from the diagram. So there's the diagram that was given to me. So one thing I do know is that the mass is 7 kilograms. So let's just record that, stick that in there, and then I've got that recorded. That's ticked off. Attached 2 springs, identical, blah, 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 that's okay. All right, so if they've got a spring constant, they'll be the same for both. Right, what's next then? The other ends of the spring are attached to 2 fixed points, 1.2 meters apart. So I can substitute that in quite easily and see what's happening. The spring's pushing on here, so this spring will push it, this spring will pull it, so it bounces that side, and then this spring will try pushing it, this spring will try pulling it. So it's got a simple harmonic motion. It's just going to keep bouncing either side of this value C. Okay, and the reason why it's on the side, this is more common than you would think. These questions are usually on the side, and the reason why they're on the side, on a smooth horizontal surface, so there's no friction acting on it, is because then you don't have to take into consideration weight. Right, we'll come back to some of those questions later. But in this case, we don't have to worry about its weight affecting it. It's just literally this ball moving left and right about the equilibrium point. So let's have a look what other bits of information I could put in. The spring has a natural length of 0.4. Now I can't really show that on my diagram because neither of these two are natural length. So I'm going to write that down, and I'm just going to record the K value as well. My spring constant is 56. So I'm just making a note of both of those bits so I can get rid of them in a second. The particle is released from rest at a distance of 0.5 meters from B. So I can put that down. Initially, it's 0.5 meters from B. Okay, initially. And so what's going to happen, as I said, it's going to bounce that way. So we've got that. It's never going to go beyond 0.5 on each side. All right, it's never going to get nearer to 0.5 to either of them because it's just bouncing freely between. Right, what happens next then? The midpoint of AB is C. So we know that that distance from there to there is C. And that's obviously going to be 0.6 because it's the midpoint of 1.2. Okay, so those 2 bits of information, bit redundant really, but let's put them both on anyway. So that's labelled C. At time t seconds after release, the displacement of the particle C is x meters. Alright, so that's where the x comes in there. That's already shown on the diagram, where the direction from A to B is taken as positive. Okay, so let's just record that then. Stick that down. A to B is taken as positive. Alright, because there must be a reason why they put that. So I've put all of those words on my diagram now. So what I'm going to do is get rid of those and put the first question back up. Show the resultant force of the particle at time t is minus 112 x newtons. So because this is to do with force, then it's more to do with, okay, it's important to remember that you can make use of your mechanics skills from your normal maths. So when we're talking about resultant force acting on a particle, there's nothing wrong with you doing a quick sketch of thinking, what are the forces acting on this particle? So the particle, you can ignore the weight because that's obviously got its normal reaction force. So we can ignore both of those. All right. But what we want to do is we want to be thinking about what other forces are acting on it. Now it's very easy to think that this spring here is pushing that particle away. It's very easy to think that this is sort of pushing it. But just be aware that if this spring wasn't attached here, okay, if this spring wasn't attached, this spring here is stretched by 0.5. Right, that's its initial stretch of 0.5. Its natural length is 0.4. It wants to be actually going in this direction. In fact, if this spring wasn't attached to it at all, this particle would actually be going that way because the spring will be pulling it back towards its natural length. So it's very easy to think that this is pushing it and this one's pulling it, but it's not the case. In fact, this spring is pulling it, but this, because it's got more extension, is actually pulling it with more force. Okay, but both of them are trying to push that particle, or sorry, pull that particle towards them. All right, both of them are. So what does that mean then? Well, it means if you look at the forces acting on this particle here, it's got a bit of tension acting in this direction. In fact, a more tension acting in this direction, where this spring is trying to pull it back towards its natural length here. And it's also got forces acting on this direction, trying to pull it back towards its natural length in that direction. It's not pushing it away. If it was beyond that 0.4, then yes, it would be trying to push it. But in this case, because both of them are longer than the natural length, they're both pulling and trying to pull that particle back towards their natural length. So we're going to use Hooke's law, T equals x kx. All right, and just to re-emphasize that point then, the x value is Hooke's law is the extension that's being beyond its natural length. Okay, that's different to the formula we looked at a minute ago, remember? So Hooke's law is the extension that's being beyond its natural length. And in this case, as we said, both of the springs are being stretched beyond their natural length. Okay, let's get rid of that. Let's just have a go at working these two bits out then. So we can calculate the distance the spring attached to A is stretched beyond its natural length. We can see that it's got 0.6. This would be 0.6 as well, and it's got 0.1 just here. So really, A is stretched to 0.7. The x value along its natural length is going to be the difference between 0.7 and 0.4. So it's got 0.6 minus 0.4x, and you could calculate that yourself in your heads. You know it's got an extra extension of 0.2. So we know that the spring is attached to A, has this tension then. 56, because that's the K value, and the X value is 0.2 plus whatever X is. Okay, now a minute ago I said it was 0.1, but that's only the initial. So we're looking at a general, what's the extension, and it's the X value. So that's the tension that A would have at any given point. What about B? Yeah, that's expanded out. What about B? So the tension for, okay, so we've got the tension for A. Now let's have a go at doing the tension for B. Just think about its extension X then. So it's got its natural length of 0.4. So the difference between the midpoint, the equilibrium point just there, 0.6 and 0.4 will be 0.2, but it's closer this time, so you're going to be minusing whatever x is from that as well. So it wants to be, it's roughly 0.2 between the extension and x minus whatever x is. So you can think of it like this. The natural length, sorry, the full length from there to there is 0.6 minus the natural length, which is 0.4, but also minus this x value gets its position. Okay, so it's like 0.2 minus x. That would be the tension at B, or tension in the spring B. So what can I do then? I could do the same as before. I can use Hooke's law. I know the K value, because they're identical springs, is going to be 56. So I can expand that out, and I get 11.2 minus 56. You expected them to be similar. You expect them to be similar because they are the same springs. All right. Once that's on this side, it does exactly the same but opposite. So you expect these two values to be very, very similar. Okay. What's the resultant force? I want to show that it's this value just here. Now we know that the resultant force, it's told us it's in a positive direction, is this way. So if I'm looking at this in the positive direction, then it's going to be TB minus this one that's pulling in the opposite direction. All right, that's why in the question it said taking A to B as positive, because they wanted to produce this negative part just here. So what do I get then? I get that value minus that value gets me minus 112 x newtons, exactly like I wanted to show. Okay, so that's where that first part came from. All right, just pause there if you need to. So I can guess that this particle is going to oscillate either side of its equilibrium point. All right, it's going to keep oscillating like that. Now I know that that's basically what simple harmonic motion is. This is moving either side of its equilibrium point, and so therefore it's going to be simple harmonic motion. But how do I go about showing it? Now the way you go about showing it is by getting or forming an equation that looks the same as the simple harmonic motion equation. The x double dot, the acceleration, equals minus omega squared x. In other words, something like the second derivative equals some number times x. That's my goal. Okay, right, what have I got to work with? Well, I'm not 100% sure what I've got to work with, but I remember the previous question got me this result. F equals minus 112x. Now I can see that that part there, minus 112x, maybe something to do with simple harmonic motion, maybe on that side. What about this side, F? Well, I know that force, F, equals mass times acceleration. So that is what I'm going to use. F equals ma. Okay, so I've got F equals ma. Now the force is the 112x, mass is 7, acceleration is my x double dot, or d squared x over dt squared. So therefore I've got my equation. That's starting to look quite similar to simple harmonic motion already. If I do a bit of rearranging then, put the second derivative at the front, that's my x double dot at the front, minus 16x, perfect. So therefore I would say that is equivalent to simple harmonic motion. And just stating that and rewriting it saying, look, that was my goal to get it into this form, then that's good enough. Okay? So therefore, just a little short statement saying that it definitely moves with simple harmonic motion. Okay, pause there if you need to. So question C then. So question C says state the period of the motion. Now that you've got its simple harmonic motion, so now you know that it's traveling under simple harmonic motion, then this part is a little bit easier. We know that the formula for the periodic time, or the period of the formula as it says there, is going to be 2 pi over omega. But also know from the previous bit of work that I have x double dot equals minus 16 over x. What does that tell me about omega? Well, omega squared is 16, so therefore omega equals 4. Okay, omega value can ignore the negative. Right, so what does that tell me then? 2 pi over 4, which is exactly the same as pi over 2. So it, as periodic time, is going to be pi over 2. Okay, just pause if you need more time. Find the speed of the particle. So now that I've got the equation for the simple harmonic motion, I should be able to then find the speed. All right? Remember in those previous sort of exercises you've been practicing, where you linked the acceleration, the velocity, and the displacement onto simple harmonic motion. That's the same with this one. Once you get past all the difficult parts at the start, it boils back down to some of the questions you've been working with. Find the speed of the particle when it is 0.3 meters from C. Okay, so we're going to use the formula V equals omega lots of a squared minus x squared. Right, the examiner expects you to know it and be able to use it. He'll also be able to expect you to show the answer without having to use that formula. So you need to be careful. But in this case, we can use the formula. It's a good chance it would give you that anyway. We can substitute in the bits we know, find the speed of the particle when it is 0.3 meters from C. So the A value is its maximum distance from its equilibrium point. Now you might be thinking I haven't been given that, but you go back to your drawing. Initially it was 0.5 meters. Don't put your initial value in as 0.5, of course. The A value is its maximum distance from the equilibrium point. So its maximum distance is going to be 0.1. It's never going to get more than 0.1. It's always going to go between 0.1 and minus 0.1, and so on. Okay, so that's the A value. The omega value we figured out as well earlier on. So there's our 0.1. 0.6 minus 0.5. So the omega value we figured out earlier on as well. So, and the x value is given to us in the question as 0.03. So I can put all that information into my equation and therefore get a velocity of 0.150 meters per second at the end. Okay, so well done if you managed to figure that out. Pause there if you need to. Let's look at the final question. Write down the expression for x in terms of t. So in other words, the displacement part. Okay, so the displacement equation. What is that x value in terms of t? So the expression for x, as you notice, is starting at its maximum point. So because it starts at its maximum point, it's appropriate to use x equals a cos omega t. Once you've got that, I can substitute in the parts that I need. So the a value is 0.1, the omega value is 4, and there's my expression straight away. Don't need to do anything more than that. X equals 0.1 cos 4t meters at any given time. Right, well done if you managed to follow that through. As I said before, that is quite a tough question. They're like the top end of some of the questions you're going to get in your further maths, but they will get a fair bit of help throughout some of the questions as well. What I'd like you to do is just have a go at one or two of those on 12B, just the rest of that exercise.